right, let's talk about logarithms. A logarithm is basically the inverse of an exponential. So you'll notice up top here that y equals log base a of x is actually just the inverse of, right? It's only true if and only if a to the y, right? So the same base, notice log base a, exponential base a to the y would have been equal to x, or what's inside that logarithm. What that gives us is a quick and easy way to convert between logarithms and exponentials. We just have to match up sort of the like parts. And the easiest part to notice is that base. Remember, log base a just means that there's multiple different kinds of logarithms, like log base 4 and log base 5. It's much like taking a square root versus a cubed root. There's different types of roots. Well, there's also different types of logarithms. And what we want to be able to do right off the bat is being able to kind of switch those out. Now, there's one easy way to do that. I like to call it the swirl or the dance. And basically, you start with the base, and we're just going to draw a swirl past the equal sign and back around to what's inside the logarithm. Again, if this is log base 4, what we're going to change it to is exponential base 4 of, again, what's on the opposite side. So again, it used to be log base 4 of x. Now it's going to be 4 raised to the, right, exponential, raised to the second power, right, over on this other side. So 4 squared will equal, again, what was inside the logarithm, which for us was just x, which means we just found a way to solve, right, that logarithm problem. Basically, x comes out to 16. Let's do the same thing with the next problem. So 5 raised to the 0 is going to equal x. So 5, again, being our base, 0 on the other side becomes our exponent, and what was inside is our x. 5 to the 0 would have been 1, so x equals 1. Also defining for us a really simple rule. Log base 5 of 1, right, when x was 1 here, that comes out to 0. And finally, 3 to the negative 2 equals x. Again, 3 to the negative 2 power, right, what was on the other side of that equal sign, equals x. And we know that negative exponents make fractions, and 3 squared is 9. So basically, we just figured out x is 1/9. Again, just an easy way to solve. Now, using those same ideas, right, we can also sort of cancel logarithms. 3, right, would over here on the right side, log base 3 is basically asking the question, log base 3 of 9, 3 to what power would be equal to 9? Right, 3 to what power equals 9? Or sometimes it's easier to rewrite that logarithm. If I can change 9 to have an equal base, right, well, log base 3 of 3 to the second power, well, 3 again to what power? Well, to the second power. Logarithms find exponents. That's basically what they do. So again, if you can change what's inside the logarithm to have an equal base with the logarithm, again, 4 to what power would be 1/4? Well, 4 to the negative 1. We know that. Negative exponents make fractions. And basically, we've solved that problem. And then the same thing goes. 9 to what power would be 3? Well, remember that 3 is the same thing as the square root of 9. And remember, square roots can be represented with exponents as well. Log base 9 of 9 to the 1/2, which means that, again, 9 to what power would be 3? Well, 9 to the 1/2 power. Logarithms find exponents. Why do we need logarithms? Well, a couple of different looks at it. Number one, to solve equations. Again, why do we need subtraction? Well, because x plus 9, the easiest way to solve that is to subtract 9 from both sides. X equals negative 14. Same thing goes over here. 4x equals 30. Well, again, if we have the inverse operation, we can quickly say, well, that's 7.5. And again, the same thing. If we take the square root on both sides, x equals, now we do have to be a little careful with that one. Don't forget the plus or minus, but we'll get plus or minus 5. Problem is on the right side, 2 to what power equals 50? Well, we know that 2 to the 4th is 16. 2 to the 5th is 32. So that's almost 50. And 2 to the 6th, though, is 64. So it's somewhere between 5 and 6, right? 2 to the 5th and 2 to the 6th sort of bookended. They surrounded that 50. But what we can do is, again, do that little bit of a swirl, right? Do that dance. If we convert this thing, log base 2 of that number on the other side will be equal to x. And we've found a way, right? Found a way to solve for x. Now, finding that log base 2 of 50, we might have to wait into the future here and get a little bit more information. But for now, we've at least found a way again to solve for x, get x by itself. Another reason is if you ever heard of a logarithmic scale, a logarithmic scale just helps us handle really, really big or really, really small numbers, right? Really, really gigantic or really, really small numbers. So sound powers, right? Over here on the left, the numbers, right? Over here on the left, the scale for different sound levels, right? The actual energy going into a sound may seem very flat compared to a jet, right? All these things don't seem very loud compared to a jet. Now, we know rock concerts and chainsaws, they're really, really loud. But compared to a jet, again, they don't seem to register. But if we use a logarithmic scale, right, similar to the one on the bottom here, the decibel scale, what it does is converts these smaller numbers, right, and don't seem really small, but converts those smaller numbers for these other sounds into a much more sort of realistic or usable, right, level, right? The jet is still much louder than all the rest. Don't get me wrong. The jet is still much, much louder. And we got a little off there on our scale. But the jet is still much louder. But again, the decibel levels allow us to sort of compare those numbers and not feel like it's just kind of crushing all those other ones, right? Not making them worth anything. Again, look more into the decibel scale, or you could also look into earthquakes and the Richter scale. There'll be another good example of, again, using numbers and converting those numbers using a log scale. Now, a few properties of logarithms, some basic ones. We already kind of looked at a couple of them. Number one, if you have the log base 4 of 4, if your log base and your exponential base, right, the exponential that's on the inside of that logarithm, if those two things are the same, basically they're just going to cancel away. And that's what our second rule over here says. Log base a of a equals 1. Or the third rule, log base a of a to the x equals the exponent, right? It equals that exponent. So log base 4 of 4 is going to cancel away and just give us 15, right? Same thing goes, log base p of p. Well, as long as the bases are equal, that exponent will be our answer, right? And it works the other way around as well. Notice, again, in rule 3 down here, a raised to the log base a. It doesn't matter the order, if it's the logarithm of an exponential or the exponential of a logarithm, as long as those bases are equal, right? Like 10 to the log of 15. Now notice there's no base written here. Well, remember, that's what we call a common log. We'll talk more about that in a minute. If no base is showing, then it's a log base 10. So 10 to the log base 10 is going to very simply be 15. You can check that on your calculator. Again, 4 to the log base 4 very simply cancels away, and this 4 that was inside becomes our answer. Again, we already looked at the rule. Log base a of 1 will always come out to 0. Again, if you don't believe it, convert that logarithm, right? That just means that a to the 0 equals 1. Or simply on rule number 2, a to the first power, right? Base a to the first power would equal a. Well, I don't think anybody's going to argue with that statement. And down at the bottom, it's basic logic. If two logarithms are equal to each other and the logarithms are the same, then what's inside that function, right, must also be the same. So if we subtract x and then divide by positive 4, we can simply solve that equation, right? Because those two logarithms are equal, they're equal to each other, what's inside needs to be equal, right? So that basically one-to-one property. An easy way to solve those logarithms. One last set of numbers here that we want to take a look at. First of all, there's two kinds of logarithms that are easy to type into a calculator. Now, it's not impossible to type the other ones, but we're going to need some more properties, some more rules. But if we know some things about common logs and natural logs, common log is just the log base 10 of x. We can also just call it log of x. So log base 10, right, of 10, well, that's simply going to be 1. Now, you can never take the logarithm of a negative number, right? Because we would say, well, 10 to what power, right, would have been equal to negative 10. Well, exponents don't turn numbers into negative numbers. We know that already, right, from our exponentials that we've studied. So this one would be no solution, right? No solution or not real, basically there. Now, if I can make log base 10, similar to what we did earlier, let's say 10 to the negative 2, right? Wouldn't that be logarithm of 1/100th? 10 to the negative 2. So therefore, the answer to this one is going to be negative 2. Now, 22 is not a simple power of 10, right? 22 falls sort of in between 10 and 100, though. So I know it's going to be 1 point something, right? 10 to the first, 10 to the second, somewhere between 1 and 2. But again, that's where I can simply type it into my calculator, use your common log button, just basic log of 22. And like we thought, this one's going to be approximately 1.324. Right? If we're going to round off to 3 decimal places, that's always a good rule, round to 3 decimal places, and you'll have that answer. Again, if you can figure out, though, a simple answer to this, right? 10 to the third is 1,000, so our answer is going to be 3. And again, don't let square roots throw you off. A square root is really just a 1/2 exponent, which means we can simply get an answer of 1/2. Realize the common logs aren't the only logarithm you can type in a calculator. The natural log is also one. Again, natural log, ln of x, okay? ln being the natural log. Again, that's log base e. So natural log of e squared is just going to be 2 here. Because again, that base e of e cancels away. The logarithm of 1, right? Again, what e to what power would be 1? Remember, that's always 0. Log of 1 is always 0. And very simply, again, if we did that little conversion, e to the other side equals x. So e to the negative 1 equals x. Or for this problem, x equals 1 over e, which again, we could always type in our calculator to find the decimal value of. I hope that helps you evaluating logarithms, using some log properties, some basic ones, and understanding how logarithms work. If you have any questions, talk to your teacher. Otherwise, have a great day.